But that's for a separate class. I want to keep talking about proofs. Darn it. So, one of the additional questions we can ask is, what other methods do we have? Because we have direct, indirect, contradiction, vacuous, trivial. But what else can I do? And when do I use what? As I said last time, it isn't always obvious what to do first, but there are several places where style, headspace, heuristic comes into play for us. So let's talk about some of these options. There's something called a proof by cases or a proof by exhaustion. Proof by exhaustion is a variant of proof by cases where you make sure you've gone through all the possible cases. And if there are only a small number of cases, you could do them each individually. So for example, here's a claim. I claim that 2 to the nth is less than n squared plus 1, where n is an integer, but more, n has to be between 1 and 4, inclusive. How many integers are there between 1 and 4? So check them. Literally, all you have to do is plug in 1, 2, 3, and 4, and you will have verified all the possible cases for this claim and thus proved it. Two to the first is, and 1 plus 1 is 2. And that satisfies 2 is less than or equal to 2. That's what I wanted. If n equals 2, 2 squared versus 2 to the second plus 1, that's 4 plus 1, that's 5. 4 is less than or equal to 5. That works. N equals 3. 2 to the third versus 3 squared plus 1. 2 to the third is 3 squared plus 1 is 10. 8's less than or equal to 10. 2 to the fourth versus 4 squared plus 1. And 16 is less than or equal to 17. That works. Those are all the possible. Ooh, doesn't help if you can't see what I'm writing. There we go. I've gone through all the possible integer values, integer, between 1 and 4 inclusive. I've shown this is always true for the universe I'm talking about. Questions? Notice that each proof, each case, was simply verifying that the sentence we wanted was true. What I've proved is that this sentence is true for all n that meet this criteria, but instead of actually proving it in variable terms, I've proved it by going through all the possible outcomes. This works really well when there are a finite number of outcomes. If I'm going to prove something applies all the time, this is probably not going to be the right way to do it. Unless I can take that huge category, infinite collection of things, and break them up into subsets. then I might be able to say, oh, well, if you're in this subset, it works this way. And if you're in this subset, it works a different way. And if you're in this subset, it works a different way. And then I would still have cases, but each case might be infinite, as opposed to each case being a single value. An example. If x and y are real numbers, then the maximum of x and y plus the minimum of x and y is the same as the sum x plus y. So that's what this symbol means, that whichever one is larger, whichever one is smaller. Now, think about it for a minute. If I give you two numbers and I say, take the bigger one and add it to the smaller one, isn't that the same as adding the two numbers together? You sure about that? I claim we can prove this in cases. But what we have to decide, here are your two numbers. Which one's bigger? So Seth, I'm going to address the idea that you had with the two people. Let's pick which is the bigger number, which is the smaller number, as opposed to which is the first person fooled, which is the second person fooled. And that's the way I'll divide up my cases. Let's suppose that x is smaller than y. Well, then on the left-hand side, the maximum of the two of them is, and the minimum is, and therefore when I add maximum plus minimum, I get y plus x, but addition works both ways. There's one case, but that case is only true when x is smaller than y. But that's not the only option, is there? What's the other option? Not a whole lot changes here, right? Max of xy now is x, and the minimum of xy is now y, so that when I add the maximum to the minimum, this time literally I'm adding x plus y in the right order, check. Ta-da! But wait, there's more. Here's a common problem in proof by cases. You have to make sure you've covered all the options. I didn't yet. What's missing?
They're equal to each other?
Ah, crud. I didn't say anything about the numbers being required to be different. So I need case 3. X equals y. Well, now I get to play. Because I know that the maximum of x and y is x, which is the same as y. So I could use either one. And the minimum of x and y is y, which is equal to x. So I could again use either one. So when I go to add the maximum and the minimum together, I can pick whichever one I want up here for the maximum. Might as well pick x. I can pick whichever one here I want for the minimum. Might as well pick y. Well, that's exactly what I wanted it to be, x plus y. I'm done. I must exhaust all of the possibilities in my cases. That's why the other name for this is proof by exhaustion. I must exhaust all the possibilities within my set. Now notice something foundationally different between these two proof by cases. The first one was finite. I checked this number, this number, this number, this number, I'm done. Because these sets are infinite, I had to do each piece as a general proof in variables. I had to do these as direct proofs, but there was no numbers anywhere involved here. Questions? Talk to me. Yes, sir. Oh, it would look exactly like that. Prove the following. Most of these get written as prove this. Show this. I claim the following. Somewhere in there, you're going to see one of those sets of words written. It'll look very much like the homework problems look for this section and for 1.7. Nope. No, you can use whatever method you want. And that's the other problem with doing proofs, period. I start with this, I'm going to get there. What path do I take in between? This is the big problem. You need to be Google. Because I'm telling you, here's the start point, here's the end point. You have to draw the map, Google. It means you need to know all the roads in the middle. You need to know what routes you can take. Gosh, there are lots of options before us. Do I do a direct proof? Do I do an indirect proof? Do I do a proof by contradiction? Do I have clear cases? I will give you hints as often as I can. I'm not expecting you to master all of these different techniques immediately. So I'll tell you, hey, maybe try a direct proof. Maybe try an indirect proof. Try a cases. I'll give you those options at this point. Because this is brand new. You've been doing this, what, a week? Proofs are 2,500 years old. I don't want you to master them in a week. Oh yeah, I'm going to do a lot more. Other questions? I want to tweak this proof just a little. If you look at case 1 and case 2, what's different about those two cases?
Greater than symbol.
And really, all it means is that since here x was smaller than y, I put the y here and the x here. Since here y was smaller than x, I put the y here and the x here. All I did was change the label, right? Really, I can change the number of cases here. I can shrink the number of cases down. And I can do both case 1 and 2 together. Because really, in these two cases, I'm looking at two different numbers. And in case 3, I'm looking at two of the same number. So let me revise this proof again. If I want to combine those first two cases, I'll start by saying, all I know is that the numbers are different. Now, Seth, here's where I get to give you the choice. One of these is bigger, one of these is smaller. Name them. You get to pick. But it doesn't matter which one you call the bigger one. It doesn't matter which one you call the smaller one. the proof works the same both ways. We just relabel things, right? Like in the fooling two people, it doesn't matter which one's person one and which one's person two. Thing one and thing two are exactly the same except for the number on the shirt, right? Dr. Seuss rolled that pictures out perfectly. I'm going to pick one. And I can do that and still have the proof be as general as possible. So the phrase we use is without loss of generality. Assume which one is going to be bigger, which one is going to be smaller. Without loss of generality, assume. And now, Seth, you have to tell me, which is the bigger number?
Okay.
I'm using X and Y. Oh, X and Y. Which one's which? Okay, assume X is bigger than Y. And now I do the proof assuming X is bigger than Y, which was in our previous version, case 2, right? So here's how sneaky I'm going to be. Look at case 1 up here, right? The only difference is which number is labeled which bigger, right? So if I change this to an X and this to a Y, then this sentence is still going to work, isn't it? But it's general enough that it works both cases at the same time. You never have to do Y is bigger than X. Because if you want to do Y is bigger than X, you just take the two numbers and switch their places. And then you write this argument exactly again, don't you? I don't care if you're Fred and George or George and Fred, it doesn't matter, it works the same way. There is still a case 2. What's case 2? They're equal. And then I've covered all my bases. But I know exactly how to write that version because we already did it. It's exactly the same as our previous case 3. And then I've covered all the options. My numbers are equal or they're not. This without loss of generality idea is exactly what we do in our existential instantiation and our universal instantiation. P of X is true for all numbers X. Okay, here's a number. Call it C. I named it. Without any loss of generality, I said from here on, C refers to this number we've already. There exists a number for which this property is true. Call that number Q. From here on out, whenever I use Q, it means that number. I have two numbers that are different. The bigger one is now named X. By fiat, you said so, we're going to run with it. If my two numbers are not different, then I'm in the other case. I'm not worried about that right now. But no longer do I have to look at bigger, smaller as two different directions, just one. Questions? I use this idea so much I end up abbreviating it. Without loss of generality assumed. Please notice that at no point in this process did I actually do an example. I never said, give me two numbers. What's the bigger one? What's the smaller one? Let's add them together and see what we get. I just didn't do that. We should try to see whether or not our idea is provable before we actually try and prove it. So if I'm going to say, should I prove this? Here's another way this question might show up. It might say prove or disprove. What do I do in that case? I should try some and see, hey, does this thing that you want me to show actually work? Or can I find a counterexample? Because as soon as you find one counterexample, you're done. Page 190, I'm sorry, not page 190, page 90, 93, 94, and 95. I've got a half a dozen different examples of proof by case, proof by generality. I've got a bunch of these in this setup. In passing, one of the bigger issues is that sometimes we have an idea as to whether or not something should work or be true. We don't know how to prove it. For a very long time, the following was a conjecture. Let's start with a map on a piece of paper. Two countries are adjacent if they share a part of their border. More than a single point. So if you think about four corners out in the Midwest, where Nevada and Utah and Colorado, and I've forgotten the other one, all meet at one spot, that doesn't count. I'm talking about the linear edges, like where Florida meets Georgia or Mississippi, where Nevada meets California, where Canada meets the US. The four color conjecture said that no matter what map you draw, take no more than four colors to color them so that no countries that are adjacent share the same color. This idea was unproven for about 200 years. I know I need at least four colors because I can draw the following map. Notice that every country is adjacent to all of the others. I have to have at least four colors. And for about 150 years, we guaranteed we could do it with five. Map makers used five colors. Nobody knew how to get down from 5 to 4 for over 100 some odd years. We had huge numbers of examples, thousands of examples, hundreds of thousands of examples that showed you never needed more than 4. That wasn't the proof. Until two computer science mathematicians by the name of Haken and Appel showed all the possible cases they did a proof by exhaustion. It was over 300,000 cases. It was one of the first computer-assisted proofs. Because what they did is they coded each map into the computer as a network of what's adjacent to what, and figured out how to represent colorings of those networks. And they talked about reducing configuration and taking out blocks you knew could be done in 4 colors and saying, well, it works here, we just have to worry about this bridge in the middle. That proof, I think, was in the mid-80s. This is fairly recent math. And over the past 45 years, the number of cases has gone from 300,000 down to, I think, about 800. The original proof was a 1,000-page book and hours and hours and hours of computer code. As a result, this is now no longer the 4-color conjecture. It's the 4-color theorem. They've proved it. I don't want to read the proof. But it was a proof by exhaustion. You should look this up. There's a really nice Nova special about the 4-color theorem. It's actually a very interesting 45 minutes of TV. Google it. I'm sure it'll come up very quick. Questions? Again, proving that they'd exhausted all the cases. That took a lot of work.
If you cut that circle in half. And
This one?
Yeah, just cut the circle in half,
Which way?
up and down. Actually, it doesn't really matter. And then just have 4 sections of, touching that half of the circle. So like cut one half into 4. One half of the circle, cut it into 4 pieces. Wouldn't, if it was on all of those, it needs more than 4 sections, because there's a section for each one?
Well, this can be colored B. This can be, depending on where this line is. I could color this one C, couldn't I? Then I could color this B. Then I could color this D. And then I could color this B.
Then what would you make the other side of it?
That's A. That's still 4 colors. You're developing something called a Kempe chain. This was addressed in part of Haken and Apel's proof.
Is that it's impossible to draw a map?
It's impossible to draw a flat map where countries are contiguous blobs and you only measure adjacency by being next to each other with a line. It is impossible to draw a map that requires more than 4 colors on a flat surface or on a sphere. That's the actual 4-color theorem. Any map that is drawable on a flat sheet of paper requires no more than 4 colors. Chew on this one. This one's fun. Every fantasy map in the universe can be drawn in 4 colors. All right. I want to move on. I promise if you really want to talk about this, we can chew on this after class. How do you prove something exists? Say that again, sir? Find an example. Sure, absolutely. Find the one that works. there is some positive integer, a positive whole number that you can write as the sum of two cubes, number to the third power plus number to the third power, in two different ways. I wish I was making the following story up. An Indian mathematician by the name of Ramanujan was brought to England by a friend, Hardy, and Hardy wanted Ramanujan to study at the university, and the racism and biases of the time didn't really lend itself to bringing Indian mathematicians to English universities, so they didn't like this idea. Ramanujan, on the other hand, was brilliant, but claimed that his mathematical insights came to him as direct visions from God. He didn't do a lot of proof, but man, did he write conjectures all over the place. Notebooks upon notebooks upon notebooks of conjecture, many of which turned out to be provable. And when he wrote proofs, he got in. Ramanujan got sick. Hardy went to visit him. And when he walked in to see Ramanujan, Ramanujan was laid up in bed looking like death warmed over. And Hardy loses his ability to figure out what should I talk about? Oh crap, how do I start this? Oh gee, you look like crap. I don't want to start the conversation that way. What do I do? And he says, I came to visit you in the worst possible cab number. The cab number on my cab was 1,729. And Ramanujan goes, that's a beautiful number. That's the smallest number that can be written as two different cubes in two different ways. Beth, how long would you have been there trying to find this number? Yeah, me too. That's a problem, isn't it? So I love the idea of, here it is. There is a number that does that. I've shown it. It's right here. I've constructed the example. That's what this is. This is a constructive proof. I built the number you want. I found the thing that does the property. But I don't know how I would have found that without starting at one and starting to think about all the different ways to add numbers up. Oh boy, would have been here forever, wouldn't it? There are other options. Now, there are lots of different non-constructive proofs that are still existence proofs. One of my favorites happens to come from Calc 1. Again, I'm going to ask, you guys got the continuity, right? Okay. First of all, what's it mean for a function to have a root? Oh, I stumped the room, damn. That's a place where the function is 0. On the graph, that's an x-intercept. I guarantee you right now, I don't know what the place is. I don't know the X value where this is equal to 0. But I still guarantee you it's got one. How do you know I'm not talking out my ass?
If it goes from positive to negative, and it's, continuous, then it has to pass through it.
Or instead of going from positive to negative, it could go from negative to positive, right? As long as we change signs somewhere, then we had to go through 0 because this is a continuous function. And continuous means no holes, no gaps, no jumps, no asymptotes, no way to miss the x-axis. There you go. It's got to be somewhere between 0 and 2. Because we went from negative to positive. Do I know what the number is? Do I care? All I said is it has a root. I didn't ask you to find it for me. So you've shown that such a thing exists without actually finding it. You've given me a restriction on the universe that says such a thing must be here somewhere. Now I can continue to narrow this down. I happen to know that if you put in 1 to this equation, what's f of 1? Oh, wait a minute. 1 plus 1 minus 1. That's positive, right? So negative to positive, instead of being between 0 and 2, it's now between 0 and 1. And you could plug in other numbers and start to narrow down where this is. By the way, if you take out your graphing calculator and you graph this sucker, second, calculate 0. Find out where this function is 0. Your calculator will start moving back and forth and narrowing in, and it'll tell you where that's equal to 0. I have no idea what that number is. I didn't even write it down. X to the third plus x minus 1. Look, somewhere between x equals 0 and x equals 1. Let's zoom in and take a closer look. Yep, somewhere in there. Second, calculate 0. It's between 0 and 1. See it put up little flagpoles? It's in here. Enter. There it is. And all it did was move back and forth until we went from positive to negative. And then it started moving back in smaller increments. So it went by tenths, and then it went by hundredths, it went by thousands and 10,000s until it ran out of decimal places. Do I care what the number is? Nope. As I said, earlier in the week, I'm going to work with numbers because they're easy to understand most of the time. What's it mean to be a perfect square?
Square root is.
Your square root is an integer. 9 is 3 squared. 7 is not a perfect square. Its square root is irrational. 16 is a square, perfect square. 49 is perfect square. I claim you can find a list at least 100 numbers long where none of them are squares. I can prove this either constructively or non-constructively. I want to do it both ways. I just want to know which one you want to see first, constructive or not. Non-constructive. Okay. If I'm looking at consecutive integers and I want none of them to be squares, then let's start with a square. Let n be a positive integer. So I start with a number, I'm going to square it. But let me think about squares for a moment. If I want to look at numbers in a row and I want none of them to be squares, it means they have to be between squares, right? Like 4 is 2 squared, 9 is 3 squared. So 5, 6, 7, 8 are between n and n plus 1 squared. So here's a list. N squared plus 1, n squared plus 2, n squared plus 3, until I get to n plus 1 squared. How many numbers are in this list? Take the first one, take it away from the second one, right? So the number of things in this list are n plus 1 squared minus n squared. Plus 1. I have to count the end. If I take away n squared, I would remove this number, wouldn't I? Oh, wait a minute, that's a square. I want to remove the square, don't I? Let's remove the square. There. That's how many numbers are on the list between here and here. I want this to be bigger than 100, don't I? I want bigger than 100 here. Bigger than 100. I have an inequality involving my n. Let's solve it. Multiply this out, I get n squared plus 2n plus 1 minus n squared bigger than 100. What happens with your n squareds? They cancel. Remember, I wanted n to be an integer, right? That means that n has to be at least 50. So, let me err on the side of caution. I'll start with 51. What's 51 squared? You own a calculator. Most of you have it in front of you. What's 51 squared?
2,601.
So I'm going to start with the number 2,602. What's 51 squared? Sorry, 52 squared.
2,704.
2007. Isn't that more than 100 numbers? There you go. I did it without constructing it, and then as a result, I could construct it. Start with one bigger than a square, bigger than 50. By the way, when I pulled a number out of thin air, it was like, well, where did you get the number from? There. The non-constructive proof actually gave me a better edge to then do the constructive part. Is one better than the other? Absolutely not. My goal is just to show, hey, does this thing exist? You can do whichever way you want. Question? What's that exclamation point mean? So there exists one and only one. All right, wait a minute. For those of you that wrote logical statements without using the exclamation point, you said there exists something that does this. Oh, and if anything else does it, it must be the thing we already named, right? So really, an existence and uniqueness is two proofs. First, you prove the existence part. And you can do that constructively or non-constructively, it doesn't matter. But then if something else does the job too, then that must be the number you already found. It is also possible to prove this by showing if you pick any other number, it's not going to work. That's the contrapositive statement. That would be an indirect part two, wouldn't it? Couple more general statements. I'm not going to do an example. These examples, unfortunately, are much longer because you really have to do two parts. Page 100, 101, I think it's examples 14 and 15. One of those is a uniqueness proof. Sometimes you start working a direct proof, you run into a roadblock. So you say, all right, well, let's go the other way. Start at the conclusion and work our way back. And maybe you'll meet in the middle. Working backwards and forwards like this sometimes helps. We have to be careful, though. Remember when we proved that 1 was equal to 2? And we did something that we weren't allowed. We have to be careful as we work from each direction. We proved earlier that the square root of 2 was irrational. So if I asked you to prove that the square root of 3 was irrational, you should be able to take the proof for the square root of 2 and adapt it a little. The issue we're going to have is instead of even and odd, we've got to now look at dividing by 3 instead of dividing by 2. So there'll be a little bit of a twist in there, but it'll be a very similar proof. So in my opinion, the best way to get good at understanding how to prove something is to read a lot of proofs so that you can take those pieces and start adapting them to the things you want to prove. There are lots of open conjectures, problems that we have yet to solve. I'm going to throw one out at you. I think you'll have fun with this one. Pick a number. If the number you picked was odd, multiply by 3 and add 1. If the number you picked was even, divide it in half. Take the new number you got, repeat the process. Claim. Eventually, no matter what number you pick, eventually, you'll hit 4, 2, 1. Get stuck in that little loop. I hope to no one's surprise, this is usually called the 3x plus 1 conjecture, but it's also known by the name of the Collatz conjecture. The fact that it is a conjecture means what? There's no proof. On computers, we've shown that if a counterexample exists, it's bigger than 10 to the 300th. But there's still no proof. Nobody's found one that doesn't work. That's not enough. One of the questions is this problem provable? And that's another thing I don't know the answer to. We'll talk about the differences between problems that are actually provable and problems that aren't, after we get through complexity, which is in chapter 3. But this is the end of chapter 1. What does that mean? No, that means a test. Homework for 1-7 is due on Monday. Homework for 1-8 is due on Wednesday. We'll have a test Friday. The review sheet has been posted since day 1 of the semester. There should be a review session. In addition to the weekly tutoring thing on Wednesdays, there should be a specific review session for the exam. We won't have class time for it, but if you have questions, come bug me in office hours. I will see you all on Monday. Have a wonderful weekend. If you came in late and I still have your homework from last time, please come get it. That's how I'm taking attendance today.